So let's get started. The problem that we actually consider is called the efficiently disseminating messages over a multi-hop wireless network. So we are basically considering a stream of packets that are coming into a source, and we are interested in to efficiently disseminating these messages to everywhere in the network. So this is a fundamental problem as well as practically interesting problem. One application being the military communication over a mobile ad hoc network. So a primary measure of efficiency that we will be concerned with in this talk is the throughput optimality. That is, we are interested in designing policies that achieve the full capacity of the network. So there is a vast literature for the unicast version of the problem when you have a single source and single destination. But the broadcast, for example, a canonical example being for such a problem is back pressure policy, that is very well known to all of you, but not so much for the other flow problem, especially for the broadcast problem. The primary reason being the packet duplications that are inherent in this kind of problems are very hard to deal with. So that is why there is no flow conservation. So the system model, our system model is fairly well known, and we use a usual system model. So our wireless network is represented by a graph GVE. Each node is equipped with an omnidirectional antenna. Packet arrive at the source are IIT at every slot at the rate lambda. And the broadcast model is that we use a local broadcast model. That is, when a packet, when a node transmits a packet, this packet is received by all the out neighbors of that particular node. Okay, and the collision model is that if two or it is also very traditional. So if two or more in neighbors of a given node transmits simultaneously at a given slot, then it results a collision at that node. So the packet doesn't get through. So we will consider only collision-free schedules, so globally collision-free schedules. So we do not allow any collision in the network, and let's call the set of all feasible node activations that do not result in any collision in the network by the set M. So this set M corresponds to the set of all independent sets in an appropriately defined the collision graph in the network. Okay, so here is this. So suppose I am given this network, and the source node is 1, and the other nodes are basically destination nodes where I would like to disseminate the packets that come at node 1 to everywhere. And there are basically 4 feasible collision-free schedules in this network, assuming primary interference constraint. So we can activate node 1, and then the packet might reach at node 2, 3, and 4. Or we can activate node 2. In that case, the packet reach at node 5 and 6. Similarly, node 3 and node 4. Okay. So although here we are only, I am showing that we are only activating a single node per slot, but this is just an artifact of this example. I mean, we consider actually multiple nodes can be activated at a slot. The only constraint being there is no collision in the given network. Okay. So now let's formulate the problem formally. So a broadcast policy executes the following 2 actions. So formally a broadcast policy is something that actually executes 2 actions at a given time slot. And what are these actions? These actions is first they activate some subset of nodes, okay, that that is feasible, that do not result in a collision. So it activates a subset of node ST that belongs to the set M subject to the interference constraint. And the second is once I have activated the nodes, I will schedule some packets over those activated nodes. That is, so I have activated some nodes ST, and each of the nodes in this set ST will transmit some packets that he has or it has already received. So now let call the random variable pi by t to be the set of all packets. So consider a policy pi, and let this random variable r pi t denote the set of all, the number of all packets received by all nodes in the network up to time t under the action of the policy pi. So what is the rate of the packet reception? So this is a limit for r pi t over t is the rate of common packet reception by all nodes in the network. So we are interested in designing a broadcast policy pi such that this rate of packet reception is equal to the arrival rate lambda, and this relation should with probability 1, and this relation should hold for all lambda less than lambda star, where lambda star is the broadcast capacity of the network. So we are interested in designing such a policy that achieves that. Yes. Yes, right now we consider only one source, but it will be, as will be clear once we go through this, there is no restriction. The policy is very general, but for simplicity right now consider only one source node. Yes. Okay. So this is the first result that we actually prove, and this is actually a surprising result. I will tell you why this result is surprising. That the problem wireless broadcasting is hard. Okay. So the first theorem is that the combinatorial version of the wireless broadcast problem, when we do not take the limit, is actually NP complete. And we additionally show that this problem remains hard even when we consider we constrain the graph to be a directed acyclic graph, and even there is no activation constraint that I actually showed. That is, at a given time slot, all the nodes can be activated simultaneously. Okay, so this is surprising. Why? Because we showed in our earlier paper in 2015 MobiHoc and 2015 Infocom and 2016 MobiHoc that this problem is efficiently solvable even when we consider a case of wireless DAGs when there is a point-to-point link. So when a node transmits only, the directed link that is actually pointed towards its receiver gets a packet. Since here we consider the point-to-multipoint link, when a node transmits and everybody in its out neighbor receives a packet, this makes the problem hard. So this simple modification makes this problem from efficiently solvable to be an NP complete problem. And interestingly, this problem that I'm actually going to describe next, I'm giving you the proof because the proof is basically one-liner. So I'll be reducing the problem. This is something called monotone not all equal 3 set to the wireless broadcast problem, the combinatorial version of the wireless broadcast problem. And what is this monotone not all equal 3 set problem? It is basically a cousin of the 3 set problem that we all know of. But here there are two qualifiers, monotone not all equal. So what is it? So we have a CNF formula. Say I have three variables in each clause, and there is no complemented variable. And we are asking the question that whether there exists a satisfying assignment such that each clause contain at least one true literal and at least one false literal. So that is why it is monotone and not all equal. So they are not all equal in each clause. So this problem is called a MNA 3 set, and this is NP complete. We show that this problem reduces to the wireless broadcast problem for this particular scenario. So consider this question that can we broadcast 2 packets from the source. So I have given this network, and this network is derived as follows. So I have 3 layers. The first layer is definitely the source. The second layer is a set of all variables, and the third layer is a set of all clauses. And the connection is very straightforward. So there is a connection from a clause to a variable if that variable appears at that clause. So this is how I actually get this directed network. And now I ask this question: can we broadcast 2 packets from the source node R in 2 slots? So suppose that we can or we cannot. So what happens to the first slot? In the first slot, everybody, and suppose the broadcast capacity of the source node is 2, and the broadcast capacity of the second node, nodes of the second layer is 1, all 1. So in the first slot, every node in the second layer gets 2 packets, and suppose let's label them in 0 and 1. The interesting that is everybody that is in the third layer will get assignment for the MNA 3 set problem, because in that case at least one node will be transmitting 0 and at least one node will be transmitting 1. So this is a very straightforward reduction to the MNA 3 set problem, and this shows why this problem is NP complete. Okay, but this is again an auxiliary result. So let's go on to the main result of our paper, that is a throughput-optimal broadcast policy. But before I describe that, let's give this graph theoretical definition of a connected dominating set. So as you may be aware of this, what connected dominating set is, but I am actually giving the definition for completeness. So a connected dominating set is for a directed graph GV and its root R is a set of vertices that satisfies the following property. That is so it is a subset of vertices such that for every node in the network there is a directed path, okay, from the source node through the connected CDS up to the destination V, such that all nodes excepting possibly the last node, that is V, is in the CDS. So such a subset of nodes that satisfies this property is called a CDS. So here is an example. Suppose I am given this simple network. So in that network there are 2 CDS, two minimal CDS that I should say. The first CDS is 1 and 2. So this is node 1 and 2. So because you can see that if I take my CDS set to be 1 and 2, every other node, say 4 and 3, they have a directed path from node 1 and 2. Similarly, there is another CDS 1 and 3. In that case, you can see that node 2 and 4, there is a directed path from node 1 and there is a directed path from 3 to 4. So there are 2 CDSs, S1 and S2, that are present in this network. And the key observation, why are you interested in this? Must be transmitted sequentially by a connected dominating set. So this is a one-to-one correspondence. So path of a fully broadcasted packet is a CDS. You can say that. So that is why I had introduced a CDS. And now let's say what makes this problem really hard, because this problem has been open for last 10 years. The main problem, I mean, and also for a couple of similar other problems, is that when we actually consider networked queues, the networked queues are generally harder to analyze because of their correlation. So here consider very simple tandem queues. I have IID arrival at the first queue, and the departure from the first queue goes to the second queue. So although the arrival to the first queue is IID, the departure, the arrival to the second queue is actually correlated to the first queue, because there will be an arrival if and only if there is a packet in the first queue. So this network queue, and you can see in a very complicated network setting, this problem gets much more complicated. So that is why it is very difficult to analyze. So this motivates us to consider a relaxed system. So it is really necessary to understand and analyze these complicated network queues. So we argue that it is not, because we are basically interested in the first order optimality metric called, say, throughput optimality. And so the question is, what is a good relaxation and which constraint to relax, so that we still retain the essential characteristics of the problem and still we can solve this problem efficiently. So this is what I'm going to do. So I'm going to relax something called the precedence constraint in a problem. So what is this constraint? So consider again general network setting. Suppose there is a packet P that is incoming at the source 1, that comes at the source 1, and there is an oracle that gives it a path. And the path, as I said before, it is a connected dominating set. And for example, suppose the path is CDS is 1 and 2. So first this packet has to be broadcasted by node 1, and then after it has been broadcasted by node 1, it reaches node 2, and then it has to be broadcasted by node 2, and finally it will be reaching all its destination. So the observation is that due to the precedence, the packet P cannot be transmitted by node 2 unless it has been transmitted by node 1. I mean, this is obvious because the packet is not been there if the node 1 has not transmitted. So we precisely relax this constraint and consider a virtual system such that when a packet comes, there is a oracle that actually gives a CDS, that is a path to the packet, and once the packet gets its path, the corresponding packet is immediately copied or is counted in the corresponding virtual queue. So these virtual queues are basically you can see these are the queue counters, and these queue counters are incremented as soon as the packet arrives at the source and the corresponding path is given. So suppose the packet P comes at the source node 1, and there is some oracle that I'll be designing that gives a CDS to be 1 and 2. So this packet is immediately copied to these two virtual queues 1 and 2 immediately upon its arrival. So I am not waiting for node 1 to transmit this packet to node 2 before I increment the queue counter. So this is my virtual system. So more formally, so what do we do? We associated a virtual queue v tilde to each node v. So this is just a random variable. And upon a packet arrival, we determine a CDS TP star of t that corresponds to the packet P, and we immediately inject this new packet to each of the virtual queues. Okay? So this amounts to basically incrementing the corresponding virtual queue counter on each of its path. And similarly, how do you actually serve the packet? The service is very easy. So we serve the packet, virtual packet, as soon as the corresponding virtual queues is not empty. So we do not care what is going on in the physical queue. So it might happen that the physical queues is basically empty, but the virtual queue is not, but still we serve this packet. Okay? So this is really counterintuitive. And we actually don't care whether the physical queue is empty or not. And so the immediate question that actually arises from this description is how do we design this control, TP star T and mu star T. So how do you give the path and how do you activate the nodes? So this comes from when you actually analyze the dynamics of the virtual queues. And as I said earlier, the dynamics of the physical queues are very complicated because of this correlation, right? We cannot transmit a packet unless it has arrived at a particular queue. But in our virtual queue construction, the way we have constructed, this constraint is simply not present. So that is why the virtual queues dynamics are extremely easy. So this is a you can think of them as a parallel queues, and they are basically one-hop linear recursion. Okay? So qi tilde t plus 1 is simply what was there at the virtual queue plus the number of arrival that I have controlled. So this is a control arrival unless a traditional setting where ai is an external arrival, and this mu it is simply the service that again I'll be designing. Okay? So note that the arrivals to the virtual queues are explicit control variable of the source, and unlike the original system, given the controls, the virtual queues are independent of each other. Okay? So this is the main thing that makes this virtual queue construction really easy to analyze. Okay, so now I have to answer two questions. Remember, we have to answer two questions: how to give the connected dominating set, that is path to each packet, and how do you actually activate the nodes. And these two control will basically come from the drift analysis. So we have a very simple virtual queue dynamics. So the natural next step is to find a control that stabilizes its corresponding virtual queues. I will analyze the physical queues later because we are really interested in physical queues, but it is a two-step process. We will be doing in two steps. So first, we basically, to stabilize the virtual queues, we choose a control that minimizes the drift or quadratic Lyapunov function that I am going to define in the next slide. So again, this is a very traditional definition, but in generally we define the quadratic Lyapunov function in terms of the physical queues. But here I will be defining the quadratic Lyapunov function in terms of the virtual queues because the dynamics is extremely easy. And now I take the drift. And interestingly, once you do the calculation, the drift upper bound is separated into two parts. The first part corresponds to the routing, okay, and the second part corresponds to the node activation. So since we are going to minimize the drift at every slot, we can actually, because of the separable nature of the objective, we can minimize or optimize each of these two terms separately. And these are the corresponding control that you actually get. So let's first consider the routing control. So again, I'm looking at this first term. Okay, so now my objective is to find a root that is a connected dominating set that minimizes this objective. And what is this objective? This is simply the weight, the minimum weighted connected dominating set. Again, this is an NP-hard problem, but I will come to this issue later. So once a packet comes, I simply find the minimum weight connected dominating set and I assign it that root. And similarly, so again, I'm just giving an example. Suppose this is a given network and these numbers represent the virtual queue lengths at a given time slot. And I have shown you there are two CDSs. The first CDS has weight 1 and 2 has total weight of 15, and the second CDS 1 and 3, so 10 plus 7 it is 17. So the path that I'll give to the packet is simply the CDS 1 and 2, right? Because it is a minimum weight. So this is how routing is done, and the scheduling is similarly done. Again, this is a independent set problem. So again, each node is weighted by the corresponding virtual queue counter, and we find an optimal scheduling is simply the max weight scheduling. Just activate the maximum weighted subset of feasible nodes that maximizes this total weight. So this is very common in the max weight activation. And again, I'm just giving an example. Again, consider the previous example. And since in this particular example only one node can be activated, just activate the node that has the highest queue length. So here I activate the source node 1, which is virtual queue length 10. Others are basically 0 or something. Okay. And here is the first theorem that we prove. So the strong stability, so under the previous routing and scheduling policy, the virtual queue counters, these random variables, sum of the virtual queue counter has a limiting moment generating function, and this implies after application of Borel-Cantil lemma that almost surely that sum of the virtual queues is grows at most logarithmic in UT, almost surely. Okay. But again, so as you can see that I'm only talking about the virtual queues here, but here we are really interested in to design a throughput optimal policy. We are really interested in the physical queue. We have to show that the physical queues are stable. Okay, but this is only virtual queue. So what is the missing link? So here the missing link I'm going to do the next. The thing is that for establishing the missing link, I have to mention one more thing, that is a packet scheduling. So that means when there are two or more packets that want to be transmitted from the same given node, physical node, which packet do I give the priority? So here we use a priority rule called the nearest origin policy. It was again proposed by Gamarnik in 1998, pretty old paper from MIT. And this is called, we actually extend this priority policy, we call the extend nearest origin policy. And the priority rule is very simple. So suppose there are two contending packets that want to be transmitted from the same node at the same time, then we basically prioritize a packet that has crossed the minimum number of hops from the source. Okay, and using this, and after lots of calculation, we can show that this is the main stability theorem, that the overall EMW policy, that the way the routing and scheduling done using the virtual queues and using the ENTO, the packet scheduling rule for the physical queues, the overall EMW policy, we call this policy universal max weight, and this policy is throughput optimal. So the proof uses a previous almost sure arrival lower bound and typical sample path analysis. So probably I'll not have enough time to go through the analysis, but here is how an ENTO policy works. Suppose I have two, so this is just an example of the ENTO policy. Suppose I have two packets P1 and P2 that want to be transmitted to the same node, this node, and the P2 packet is coming from the source S2, which is 1 hop away, and the P1 packet is coming from source S1, which is 2 hop away. So according to the ENTO policy, it will give priority to the packet which has crossed the least number of hops, right? So extend nearest origin policy. Now the proof idea, so here is just a proof. So roots are fixed at the source. The basic thing we have to establish is that the total arrival at a source is basically less than equals to the total departure, that is the total service allocated to the source plus a fudge factor, and this fudge factor is of the order of log t, which will go away when you divide it by this thing by the time. So the proof actually uses stability of the virtual queues that we have already established in the previous theorem, and the Skorokhod map representation for the queues, and then the almost shear lower bound, almost shear bound that we actually established to, we have this equation, and this equation holds almost surely, and finally we use a property from the extended nearest origin policy that proves that basically using the universal stability policy to show that the physical queues are stable, rate stable. So here I will be showing some numerical results. So again, just as a proof of concept, you consider the following network without any interference constraint. So suppose there is no interference, every node can transmit at the same slot. So as you can see, for this particular example, the broadcast capacity is 2, and you can see that the asymptote lies at the rate 2, so it is fully capacity achieving. A slightly more interesting example, this one, where I have this 3x3 grid network, and I have a wireless constraint, and also not only that, the nodes are either on or off. So at a given time slot, there is a stochastic, there is a background stochastic process such that the nodes are on and off IID with some probability P1. And here I have taken three cases, that is P1 is 0.4, 0.6 and 1. And you can show that these numbers, the asymptote, the vertical asymptotes are basically the capacity. We have shown that in the paper. So this policy is capacity achieving, and as P1 decreases, naturally the delay curve shoots up earlier. So here is a conclusion. So our understanding of network control theory has progressed enormously over the last 25 years, beginning the seminal work of Tassilas and Ephraimites. So what we have done, we have designed a throughput optimal policy for broadcasting in wireless networks with point to multi-point links, and it uses a precedence relaxed virtual network framework, and we used it to solve this problem. And this framework is pretty general. For example, we have papers from Infocom that uses this framework to solve other problems, for example multicast and the generalized flow problems, and it provides a new analytical and policy design tool which might have far-reaching consequences. With this, I would like to conclude my talk, and if you have any question, you can ask me now.